So, welcome back to lectures on engineering mathematics 2, and this is lecture number 16 on Cauchy integral formula. So, today we will cover the Cauchy integral formula for simply and multiply connected domains, and then we will move to the derivative of analytic functions. In terms of the integral, we will see that we can find the derivative of an analytic function, and then we will go for some evaluation of complex line integrals with the help of Cauchy integral formula. So, just to recall, in the last lecture we have gone through the Cauchy integral theorem, which says that if f z is analytic in a simply connected domain D, then every simple closed curve C in D, we have this closed integral of f z of this analytic function over a closed path is 0. So, that was the Cauchy integral theorem, and we have gone through several examples or applications based on this theorem for the evaluation of complex line integrals. So, today first let me just tell you that this Cauchy integral theorem, there is a called the reverse or the converse of this Cauchy integral theorem. Just to mention, we are not going into the detail, we will directly move for Cauchy integral formula. So, this Moreira theorem says that if f is continuous in a simply connected domain D, so we are not talking about analyticity now. Here in the Cauchy theorem, it was like f is analytic, then we have this integral 0. Now, we are going other way around, that if this integral is 0, so we have the assumption that f is continuous in a simply connected domain D, and if we note that this integral is 0 for every closed path C in D, then f is analytic. So, that way this is a converse of this Cauchy's theorem, because from the integral now we are telling that f is analytic in D, whereas in Cauchy theorem we say this f is analytic, then this integral is 0 over any closed simple closed path C. So, this is just to mention that there is a converse of Cauchy theorem as well. So, we will move to now the Cauchy integral formula. So, there is a difference, we were talking about the Cauchy integral theorem, now we are talking about the Cauchy integral formula. So, what this formula says, that if f is analytic in a simply connected domain D, so the similar assumptions what we have for Cauchy theorem, then for any point z0 in D and any simple closed path C we take in D that encloses this point z0, we have this result that fz over z minus z0. So, this is the extra term here. If this is not there, then integral over this C f z dz was 0, but we have now z over z0. So, as a integrand, so integrand is now here this f z over z minus z0. This is no more analytic in that domain, because in the domain this z0 point is there, which is enclosed by this curve C. So, naturally this integrand is not analytic, and we do not have this as equal to 0. So, which was the case earlier when your integrand was analytic. So, here the integrand is not analytic because of this term z minus z0, and as a result this integral has the value 2 pi I and the function at z0. So, this is what we call the Cauchy integral formula. So, it has a various applications for evaluation of such integrals where the integrand is not analytic, for instance. So, this formula sometimes we also write in this form, that f at 0. So, this 2 pi I we can bring to the right hand side, and then this is a integral over this closed path of this f z over z minus z0 dz. So, going to the quick proof of this, we can consider this integral here f z over z minus z0 dz, and then we add here this term f z0 and subtract this f z0. So, again we are with this f z over z minus z0, and then we can write down it as, so f z0 the first term, and here we have 1 over z minus z0. For the second one, we have this f z minus z0 and then z minus z0. So, we have broken this integral into two parts, and we know already the result we have seen in previous lectures, that the result of this 1 over z minus z0 dz was 2 pi I. So, the first integral we have evaluated already, it is f z 0 and into 2 pi I. The second integral over this closed curve C f z minus f z 0, z minus z 0 we will evaluate now. So, we have the situation here that this integral we want to evaluate, and we consider now the situation around this z 0. We take a circle of circle which we are calling it k here, of radius rho, and the rho is less than delta, and what is the delta we will see now this connection here. So, f z is analytic and therefore continuous, that is of course, and hence for given. So, since this f z is continuous, so we can use this definition of continuity for a complex valued function. So, here for given epsilon we can always find a delta such that this difference f z minus f z 0 is less than epsilon for any z in this disk here, z minus z 0 less than delta. So, these epsilon and delta are from the definition of the continuity, since f z is continuous. So, for any given epsilon we can always find a delta such that this relation holds. And now, we have enclosed this point z 0 by a circle whose radius is rho, and rho is even less than delta. So, for given delta now we can choose a rho where rho is less than delta, and we can enclose this z 0 by this circle of radius rho. So, using now the principle of deformation. So, just to recall what was the deformation, that instead of taking this integral over the C, we can also do that over any other curve, and then the value will be the same. This is what we have learned before. So, that integral, that deformation principle says that this integral f z minus z 0 over z minus z 0 dz will be equal to f z minus z 0 over z minus z 0. So, that we have already learned. So, while making a cut there, and then we have considered this as a simply connected domain where the function, the integrand is analytic, and then we have got this result which says that the integral over this closed curve C, the value of this integral will be equal to any other path we can take inside this domain, and the value will be equal. So, that part was already discussed. So, what we observe now here, that this integral is equal to this integral, and this is going to be a simpler integral because we are talking about this k, which is a circle there. So, k is a circle of radius rho, and the rho we have taken less than delta. So, now we will make use of this inequality, that f z minus f z 0 over z minus z 0. So, on this circle k, this z minus z 0, the absolute value of this z minus z 0, the modulus of z minus z 0 is rho. So, this z minus z 0 is replaced by rho, and then from the continuity of f z we have already this relation that f z minus f z 0 is less than epsilon. So, we have this inequality here, that epsilon we can bound this integrand of this integral by epsilon over rho. And now, so this is already discussed, that this is epsilon, and then we are exactly on the boundary of this k. So, that can be replaced just by rho, and here the upper one we have just bounded it by epsilon. So, with this bound we can observe that we will use this Hamel inequality, which was also discussed in previous lectures. So, this f z, the absolute value of this integral is bounded by m into the L. L is the length of the curve, and m is the upper bound for this integrand. So, we have already the upper bound for the integrand. That means, this we can bound by this epsilon over rho, that is the bound for this integrand, and then 2 pi rho, that is the circumference of this circle k. So, 2 pi, and the rho was radius. So, the arc length of the curve, that is 2 pi rho. So, if this is simplified, this is coming 2 pi and epsilon. So, now the point is that this integral, the value of this integral, the absolute value of this integral is bounded by 2 pi epsilon, and we should note that this epsilon was arbitrary. So, from the continuity of f z we have said that for a given epsilon. So, epsilon can be chosen as small as possible, arbitrarily small. So, what this says that if this can be chosen arbitrarily small, the value of this integral is going to be 0, because the value of this integral is bounded by 2 pi epsilon, and we are telling that epsilon can be chosen arbitrarily small. This means that the value of the integral has to be 0, otherwise it cannot be less than this 2 pi epsilon, and epsilon is arbitrary number. So, now from this breakup of the integral, the first part already was evaluated, which was 2 pi I f z 0. The second, we have seen that this is going to be 0. So, we have this result, which is the Cauchy integral theorem, that this integral value is equal to 2 pi I and f z 0. There is an extension for this for multiply connected domain, because so far we have seen that the result is valid for simply connected domain. Now, if we have the multiply connected domain, now the outer curve here is traced anti-clockwise, and the inner one we have taken the clockwise direction. So, in that situation, the result says that f z 0 is equal to the first integral over the C 1 and plus over the C 2. We can have many such holes there. So, like this is like C 1, then we have here another curve C 2, the hole in this, then we have C 3, so then we have C 4 and so on. So, if we can have many such, so for the inner circles we should have the clockwise direction to happen for this result, which is a sum of all these curve integrals. So, the outer integral should be in the anti-clockwise direction, and then if the inner one are in the clockwise directions, then we can simply add these integrals and the value will be equal to f z 0. So, having this, I should make one more remark, that what will happen if we take for instance this also in the anti-clockwise direction. If we take C 2 in anti-clockwise direction, then this plus sign will become minus sign, and we will have this f z 0 equal to this, and this minus 1 over 2 pi integral over C 2. So, that is also possible. So, if we are taking in the clockwise direction, these two will be added, otherwise we can also subtract these results. Okay, well, so we can now move for the evaluation. So, we evaluate this integral tan z over z square minus 1, and then we have here z is the absolute value z is 3 by 2. So, in that case we have a integrand which is matching with this integral formula. So, in the denominator we have this z plus 1 z minus 1, and we should look now for the singularities of this f z, the integrand, f z is the integrand. So, naturally the z is equal to 1, z is equal to minus 1, we have the problem in the integrand, because this will go to 0 in either situation, and then this pi by 2, 3 pi by 2 and so on, the 10 function will become infinity. So, at all these points the function is not differentiable, or function is not analytic at those points. So, we call these points as singular points of this f z of the integrand. So, because we want to identify that where the function is not differentiable or not analytic, otherwise if the function is analytic everywhere, it is straight away we can use the Cauchy theorem and the value will be 0. So, now the situation is that this pi by 2 and 3 pi by 2, because here the radius of this circle here is 3 by 2. So, only these 2 points lie inside, that is z is equal to minus 1 and z is equal to plus 1. The all other points like pi by 2, which is pi is more than 3. So, 3 by 2, that is outside the domain of concern, outside the C. So, here this pi by 2, 3 pi by 2, they are not at all in the domain. So, not of our concern, but here z is equal to minus 1 and z is equal to plus 1, these 2 points are inside the circle C, and therefore, they will be considered now as the point of where the function is not analytic. So, here now we have 10 z over z square minus 1, we can write z minus 1 and z plus 1, and then we can have this partial fraction of the two, 1 over z minus 1 and 1 over z plus 1, and the half, the first integral is 10 z over z minus 1, the second integral 10 z over z plus 1. So, now we have exactly in the form of this Cauchy integral formula, where we can directly apply the result. This is like f z over z minus 1, and this 1 is exactly the point inside the circle here, and z equal to minus 1 is also inside the circle. So, here we have the half is already there, then 2 pi I because of the formula, and 10 has to be evaluated at 1. So, this 10 has to be, this f z has to be evaluated at 1. Similarly, for the second part we have minus half, 2 pi I and 10 here must be evaluated at minus 1. So, this is the final result, that 2 pi I and 10 1, 2 pi I and 10 1, this is the answer of this integral which we have evaluated using the Cauchy integral formula. Well, so there is another one, the derivative of analytic function. The derivative of analytic functions, the formula is quite similar to what we have seen as a Cauchy integral formula. So, if f z is analytic in a domain D, then its derivative at any point z equal to z 0 is given by this formula here, that f, the nth derivative at z 0 we can compute by this line integral factorial n over 2 pi I, and we have f z over z minus z 0 power this n plus 1 and d z. So, that is has a nice applications, and a very interesting fact that the derivative of this function which is analytic we can compute with the help of such integral, such a curve integral. Okay, so here the C is a simple closed curve in D enclosing the point z 0. So, that is the only condition, we can take any C which encloses this z 0 point, and it is in this domain D where your function is analytic. That is the only condition we have. So, using this Cauchy integral formula we can realize the above result. So, the Cauchy integral formula says that f z 0 is 1 over 2 pi I, and the integral f z over z minus z 0 d z. From here we can derive its first derivative, and then it can be generalized. So, for the first derivative, let us just make an increment here f z 0 plus delta z, and then we will apply the fundamental theorem of differentiability. So, f z 0 plus delta z, we have made this increment delta z naught. So, 1 over 2 pi I, the integral f z over this z is replaced with z naught plus delta z naught. So, here instead of z naught we will now make z naught plus delta z naught. So, z minus and z naught is replaced by z naught plus delta z naught. So, this is the result now of f z naught plus delta z naught, and we can look at this difference now, f z naught plus delta z minus this f z naught by this integral. We can have now 1 over 2 pi I f z, and this 1 over the first term z minus z 0 minus delta z naught, and then the second one 1 over z minus z naught. So, we can simplify this now, these two can be simplified to have this f z divided by this the product of the two, taking this LCM, and then we can have just one there. So, 1 over 2 pi I, and then we got this f z over z minus z naught minus delta z naught, and this product of this one. So, now if we take the limit as limit delta z approaches to 0 or delta z naught approaches to 0, what will happen to this, and that is exactly precisely the derivative of this f z at the z naught. So, taking this limit, what we will now observe here. So, we have 1 over 2 pi and this integral, and we want to take this limit delta z approaches to 0. So, what will happen when delta z approaches to 0? This is exactly becoming z minus z 0 and z minus z 0 whole square we are getting, and now this everything is free from delta z naught. So, we got this formula for the derivative that f prime at z naught is 1 over 2 pi I and f z over z minus z naught whole square. Well, so this is just for the first derivative, and then we can go for, in a similar way we can approach for the higher order derivative, which we are not doing now, but we have now the idea that how this derivative is written in terms of the integral using Cauchy integral formula. So, since this z 0 is arbitrary, we have chosen just an arbitrary point z 0, the derivative of f z of all other orders are analytic in D. So, what we have seen, if f z is analytic, we can get this f prime also at any point there in the domain. So, all order derivatives of this f z will be also analytic in D if f z is analytic in D. So, that is a very interesting result in this connection of the complex variables, that if this f z is analytic in D, then all its derivatives will be also analytic in that domain D, which is readily proved from this result, where we have seen that the derivatives can be computed easily once we know that this f z is analytic. Okay, so, we will now go through this example. We will evaluate here e power 2 z over z plus 1 power 4 d z, and here the curve is absolute, this modulus z equal to 3. So, it is a circle, center 0 and radius 3. Cauchy integral formula says that the third derivative we can evaluate by this factorial 3 to pi I e power 2 z and z plus 1 power 4. So, this is exactly z plus 1 power 4 here, and this is our f z. So, with this formula we see connection to this integral, and now we can proceed with this, taking this f z as 2 power z and its third derivative when we evaluate at this z naught point. So, we will get exactly the result of this. So, here this z minus z 0 power 4. So, z 0 is like minus 1, and we can evaluate the derivative. So, f z is e power 2 z, z 0 is minus 1, n is 3. First derivative is 2 times e power 2 z, its derivative at minus 1 we can evaluate, that is 2 over e square. Then the second derivative we can evaluate, that is 4 over e square, and then the third derivative we can evaluate at 8 over e square. So, the third derivative we need for the value of this integral here, and this third derivative then we can put there in the integral. So, this is the third derivative and equal to factorial 3 2 pi I e power z z minus z naught power 4. So, this is the value of the integral. Then this the factorial 3 over 2 pi I we can bring to the right left hand side. So, we are getting the value of the integral as 8 pi I over 3 e square. So, this was a direct application of the Cauchy integral formula, where we can get the value of such an integral. Another example where we will evaluate e power z t z square plus 1 d z, and here the circle is given by absolute value z, modulus z equal to 3. So, again we have a circle, center 0 and radius 3. So, if we see the singularity here z square plus 1, we have z plus 1 and z equal to I and z is equal to minus I. So, at these 2 points the function is problematic. So, we will proceed now writing this as a partial fraction as we have done in one of the earlier example. So, e power z t, then we have 2 I and then this is the partial fraction, 2 I will be there when we write down in terms of z square plus 1. So, that will cancel out. So, this is the partial fraction we have for 1 over z square plus 1. So, now we have these two integrals over z minus I and z plus I. In both we can use the Cauchy integral formula. Here the z naught is I and here z naught is minus I. So, z naught is minus I. So, in both we can use the Cauchy integral formula, and that says that 2 pi I and the value of the function e power z t, and that means z is I here and here z is minus I. So, we got this formula which can be also written in terms of the sine function. So, 2 pi I and then e power I t minus e power minus I t over 2 I we can write down as sine t. So, this was the one approach. For instance, we have proceed where we have applied this formula, the integral formula, to get this 2 pi I and sine t. The another approach could be that we can think of as we can take two more circles that encloses these 2 points z is equal to I z minus I. So, let us call it as C1 and the another curve here we can call it as C2. So, these two curves C1 and C2 and the outer one was the given one, the C1. So, we have drawn two more circles C1 and C2 enclosing these two problematic points, and then we can write down using this extension for the multiply connected domain that this C, the given integral, the f z, I am talking about the f z is the whole integrand. So, this is whole integrand here f z at present. So, I can write down that this integral over C will be integral over the C1 and plus C2, and doing this setting now. So, over C1 what I will do, when I do over C1 I will take z minus I and the rest I will write down e power z t divided by z plus I, because now this numerator is analytic and here z minus I is exactly fitting into the formula of the Cauchy integral. So, plus when I do the integral over the C2, what I will do now e power z t, and I will take here z minus I as my function which is analytic, and here I will do this z plus I, and then I have here dz. So, this is another approach. So, this is method 2, which where we do not have to use, for example, the partial fractions. We can just write down the given integrand in this form e power z t over z plus I and z minus I, and in this for the second curve we can use z plus I. So, this is the for multiply connected domain we have seen the integral formula, and that idea we have applied here. So, then in the first case what we have, this is has to be evaluated. So, 2 pi I and the numerator will be evaluated e power z. So, z is I now. So, I t and then divided by z is I. So, I 2 I, and then again here 2 pi I will come. So, e power minus I t and minus 2 I. So, this again can be just written as 2 pi I and sine t. So, this is another approach where we can avoid doing this partial fractions. So, directly we can compute this partial fraction without computing partial fractions, we can use the Cauchy integral formula. So, another example where we have sine 6 z and z minus pi power 3. So, here we can use so here sine z is sine 6 z and we will apply exactly the Cauchy integral formula, which is the extension to the derivatives. So, z0 here is pi by 6 and n we will take 2. So, that here we are getting exactly 3 n plus 3. So, this was the Cauchy integral formula, here 2 plus 1, if it is 2 here the derivative is second derivative. So, this is fitting exactly to the given integral. We can compute with this computation of the second order derivative. So, f prime z is already with sign 6 z we have computed here, and we can do this computations once again for the second derivative, and we can evaluate this at pi by 6. So, the value is coming 21 by 16. So, here if we write 21 by 16, this is the value of the given integral using this derivative formula of the Cauchy integral. So, the last example where we have again the similar situation, the z square minus 1 is coming, and this is with center at 1 0 and then the radius is 1. So, singularities again here we have z plus minus 1. So, the minus 1 is outside this circle at center 1 and then the radius 1. So, we have only one singularity which is coming inside this, z is equal to minus 1 is outside. So, that is not in the picture. So, what we can do, the first approach could be that we can break again into the partial fractions and then each integral can be evaluated. Indeed, the second integral here where we have z plus 1. So, the integrand here is analytic because z is equal to minus 1 is outside the domain. So, here this is analytic in C and inside C, on C and inside C. So, this is analytic, and the Cauchy integral theorem can be used here to and the first one we have to use the Cauchy integral formula, and second one we can use the Cauchy theorem. So, it says that this plus this 0 and the total answer we have 2 pi I. Or another approach, it could be that the given integral. So, the second approach could be that the given integral we can write as 3 z square plus z over this z plus 1 altogether, and then we can replace z minus 1 and then dz. If we consider this integral now, so this will be our function and divided by z minus 1, because this is now analytic in our domain. So, no problem, and then we can apply exactly the formula 2 pi I, and this has to be evaluated over z is equal to 1. So, here we have the 4 over and then 1, that means 2. So, this 2 gets cancelled and we have 4 pi I. So, this could be the another approach where we do not have to do these partial fractions unnecessarily. We can just simply rewrite our integrand so that the numerator everything is analytic, and this z is equal to 1 was the problematic point. So, we have divided by this z minus 1 and we can evaluate this. So, here we have the references which are used for preparing the lecture. Just to conclude now, so we have learnt about the Cauchy integral formula, which is very useful for evaluating the integrals, and we have also seen the derivative formula, which is exactly the kind of extension of this, or we can say this is a particular case, let us say when we put n equal to 0, because putting n equal to 0 and factorial 0 if we take 1, we are exactly getting this formula. So, this is a particular case of this more general derivative formula, and here we call it Cauchy integral formula, not the Cauchy integral theorem. The Cauchy integral theorem was when the integral was 0 and the integrand was analytic. So, with this